8. Entropy Analysis. Welcome to Chapter 8, Entropy Analysis. This chapter is where thermodynamics gets really exciting, because we go beyond just energy quantities and start thinking about the quality of energy. Entropy is like a measure of disorder, but more importantly, it tells us how useful or usable energy really is. You'll notice that no process in nature is 100% efficient, and entropy helps explain why. Whether you're studying engines, refrigerators, or even biological systems, entropy gives us a way to quantify energy losses and inefficiencies. Think of it this way. Energy is conserved, but entropy always increases in real processes. And that's a big reason why no engine is perfect, no fridge can cool without some extra work, and why the world naturally moves towards more disorder unless we intervene with more energy. By the end of this chapter, you'll be able to calculate entropy changes, understand entropy generation, and perform basic entropy balances for common devices. This is the key step in becoming a true thermodynamics thinker, someone who doesn't just track energy, but understands how to use it wisely.
1. Learning outcome. Before we dive into the details, it's important to understand exactly what you'll be able to do after this chapter. Learning outcomes give you a roadmap, showing you the skills and knowledge you'll gain. First, you'll learn how to examine reversible steady flow work, which basically means understanding ideal work scenarios where no energy is wasted. Next, you'll explore how to minimize compressor power input, which is crucial because compressors are energy-hungry devices, and optimizing them can save a lot of energy in real-world systems. You'll also be able to define isentropic efficiency for turbines, compressors, and nozzles. Isentropic efficiency tells us how close a real machine gets to an ideal performance, so it's a key metric in engineering design. Then, you'll develop the entropy balance relation, which is the mathematical tool we'll use to track entropy in open and closed systems. Finally, you'll learn to perform entropy analysis, which is about spotting inefficiencies by quantifying how much disorder or wasted energy is generated in a process. By the end of this chapter, you won't just know what entropy is, you'll know how to use it to design better, more efficient systems.
2. Reversible steady flow work. Here, we explore the idea of reversible steady flow work. The big takeaway here is the amount of work a system can do depends not just on where it starts and ends, but also on the path it takes to get there. If you want the maximum work output, it only happens in quasi-equilibrium, which basically means everything changes slowly enough that we can control it perfectly. We also introduce a key formula, the steady flow work equation. This equation shows that the work is tied to specific volume and the pressure change. The smaller the specific volume, the less work it takes to compress something. This is why, for example, compressing liquid water takes far less work than compressing steam. In fact, compressing saturated liquid requires around 500 times less work compared to saturated vapor. This idea helps engineers save energy. We want to reduce specific volume when compressing and increase specific volume when expanding. It's a simple trick with a big payoff in real-world applications, from power plants to refrigeration systems.
3. Minimizing compressor work. Here's where you'll learn how to save energy during compression processes. The main idea is simple. If you want to reduce the amount of work a compressor needs, you should cool the gas as much as possible while compressing. We look at 3 cases. First, isentropic compression means no cooling happens. This results in the highest work input. Then, polytropic compression allows some cooling, so you need moderate work input. And finally, isothermal compression provides maximum cooling, giving you the lowest work input. The practical takeaway is that if you want to make compressors more efficient, you can use multi-stage compression with intercooling. This means you cool the gas between stages, which reduces the total work needed. And for two-stage compression, there's even a shortcut formula. The optimal intermediate pressure is simply the square root of the product of the inlet and outlet pressures. This keeps your system balanced and your energy costs down.
4. Isentropic efficiencies of steady-flowed devices. Let's talk about how we measure efficiency in real machines. Isentropic efficiency is the benchmark. It compares the actual performance of a device to a perfect, loss-free isentropic process. We use different formulas depending on the device. For turbines, we look at how much actual enthalpy drop we get compared to the ideal enthalpy drop. For compressors, it's the opposite. We measure how much extra enthalpy we need because of inefficiencies. For nozzles, we use velocities to track how much kinetic energy is achieved. In real life, well-designed turbines often have efficiencies above 90%. Those smaller ones can drop to 70%. Compressors are usually a bit less efficient, generally between 80 and 90%. Why does this matter? Because these numbers show how close we get to ideal performance and where improvements can be made. Higher efficiency means less energy wasted, and that's always good engineering.
5. Entropy balance. Now we shift our focus to entropy balance, which helps us measure how much disorder or inefficiency is happening inside a system. Entropy generation is like a red flag. It shows us where irreversibilities happen, like friction or heat transfer across temperature differences. The key tool here is the entropy balance equation. It tracks how entropy comes in, how much leaves, and how much is generated due to losses. In steady-state systems, where conditions don't change with time, we simplify the equation to relate entropy flows at the inlet and outlet, plus any entropy added through heat transfer. There are two main ways entropy moves in a system: heat transfer and mass flow. With heat transfer, entropy increases when heat moves from hot to cold areas. With mass flow, entropy is simply carried in or out by the moving fluid. An important point: work doesn't transfer entropy. You can think of work as clean energy, while heat and mass flow carry the messiness or entropy of a system. By using this balance, engineers can pinpoint where energy is being wasted and design systems to minimize it.
6. Entropy balance for closed systems. Here we focus on closed systems, meaning no mass enters or leaves, and we track how entropy behaves within these boundaries. In a closed adiabatic system where no heat crosses the boundary, any change in entropy directly equals entropy generation inside the system. This is key when analyzing isolated processes. But when heat transfer happens, we look at total entropy generation by adding up entropy changes in both the system and its surroundings. This gives a complete picture of the overall inefficiencies. Some classic examples include heat loss through walls, which always increases entropy, mixing of fluids, where disorder naturally rises, and entropy generation in turbines or compressors, which tell us where mechanical inefficiencies happen. By calculating this, engineers can spot problem areas and work to reduce energy loss, making systems more sustainable and cost-effective.
7. Entropy balance for control volumes. Now we move from closed systems to control volumes, which are open systems where mass flow happens across the boundaries. This changes how we handle entropy calculations. The general entropy balance for a control volume accounts for entropy entering and leaving through both heat transfer and mass flow. It also includes the change in entropy inside the control volume over time. For steady flow devices where properties don't change with time, the equation simplifies. Entropy generation depends on the difference between inlet and outlet entropy and the heat transfer across temperature levels. In adiabatic steady flow devices, where there's no heat transfer, it gets even simpler. Entropy generation is just the difference in entropy between the exit and inlet, carried by the mass flow. This slide shows how we adapt entropy analysis when mass flow is involved, making it a crucial tool for analyzing turbines, compressors, nozzles, and heat exchangers.
8. Applications in special topics. Let's look at a practical example. Compressed air, which is widely used in industries, but often wastes a lot of energy. Compressed air systems can lose more than 50% of the input energy due to inefficiencies. That's a huge cost, both economically and environmentally. But there are simple strategies to cut these losses. First, fix air leaks. Even small leaks can drain a lot of energy. Then, use high-efficiency motors to reduce electrical consumption. Another quick win is to optimize compressor pressure settings, because higher pressures mean more work and more energy waste if not needed. We can also use intercooling and multi-stage compression to reduce work input by cooling air between stages. Finally, a great way to improve efficiency is to recover waste heat from compressors and use it for heating in the plant. These small steps can lead to significant savings and lower carbon footprints. This is how entropy analysis goes from theory to real-world impact, helping us cut waste and improve energy efficiency in industry.
9 key takeaways. Let's wrap up with the 5 biggest takeaways from this chapter, so you know exactly what to remember. First, work in compression and expansion can be minimized simply by selecting the right processes, like using cooling or multi-stage setups. Second, isentropic efficiency is your tool to compare how real machines like turbines, compressors, and nozzles perform compared to the perfect ideal case. Third, entropy generation tells us where inefficiencies happen by measuring irreversibilities like friction and heat losses. Fourth, entropy balance equations are essential tools. They allow you to calculate entropy changes and spot inefficiencies in any thermodynamic system. And fifth, in practical terms, reducing energy waste in compressed air systems can bring major cost savings, sometimes cutting energy bills in half. By understanding these 5 points, you'll not only pass your thermodynamics course, you'll also be able to design more efficient systems in the real world.
10. What you learned. Let's quickly recap the most important lessons from this chapter, so you have a clear summary in your mind. First, entropy always increases in real processes. That's why no engine is 100% efficient and why losses are unavoidable. Second, cooling during compression can significantly reduce energy use and make processes more efficient. Third, throttling, like what happens in valves, generates the maximum entropy, which means it's a highly inefficient process. Fourth is isentropic efficiency is your tool for measuring how close your system is to the ideal case, especially for turbines, compressors, and nozzles. And finally, entropy balance is your accounting method for energy dispersal. It helps you track where energy becomes less useful in any system. These 5 points summarize why entropy is more than just theory. It's a powerful concept to improve real-world energy efficiency.